Topic 3.1 is on intermolecular and interparticle forces, but here I want to look at a couple things that the book didn't cover or didn't focus on, or just explained slightly differently than the way some of the AP Chem problems might look at it. So that's why I title it Miscellaneous. So boiling point and intermolecular forces. In general, stronger intermolecular forces will increase the boiling point. So if we're looking at some aqueous solution, compounds in an aqueous solution when they'll boil off, or a pure liquid, either way, the boiling point is higher as the intermolecular forces increase in strength. Again, in topic 3.1, we're not really considering, though, we're considering molecules and intermolecular forces. We're not really considering other sorts of liquids, such as, for example, if we had like liquid NaCl. That's not really the focus of topic 3.1. We'll talk about that in other sections of this unit. So I'm just focusing on those problems right now. So if given two compounds and predicting which will have the higher boiling point, or for something similar, explicitly identify all intermolecular forces occurring in an aqueous solution or liquid of a certain chemical. So what do I mean by that? I mean, for example, if you're looking at water. So if we have water and the question says to identify what intermolecular forces are occurring, you might be tempted to just list hydrogen bonding. Do not just list hydrogen bonding, because that is not all the intermolecular forces that are occurring. You should also additionally list dipole, dipole, and London dispersion forces, because those are also occurring. Okay? So list all the forces that are occurring. If, for example, we have a polar molecule that can do dipole-dipole, you should also list LDF. And if there's a polar molecule and a nonpolar molecule, you can list LDF and you can list induced dipoles. So it's very important to mention all the different intermolecular forces that could be occurring, not just quote unquote like the strongest ones. Okay? So as I said here, you have to think about LDF, induced dipole, dipole-dipole, and hydrogen bonding. If, for example, water, don't just say hydrogen bonding, list LDF and dipole-dipole as well. That's very important, otherwise you probably won't get the point if it's like an FRQ, for example. So for example, just looking at this idea of explaining differences in boiling points, which compound on the right has the highest boiling point? Explain. So we look at these, we can see they're all nonpolar, all carbon-hydrogen bonds. So none of them are doing hydrogen bonding. None of them have dipole-dipole interactions. So it's purely which has the strongest LDF, right? So which one would that be? Pause to think about it if you need to. You should say butane because it's the largest. Now, you should say, in an answer like this, you should come out first and say, all the compounds just have London dispersion forces. However, butane has the strongest London dispersion force here. And you can use the language, it has the most electrons because it's the largest molecule, and therefore a more polarizable electron cloud. A lot of the AP Chem rubrics or explanations like that terminology, so I suggest you use it. It is a more polarizable electron cloud the larger the molecule is. Boiling point and gas vapor pressure. This is another thing that you should get from the book, but I just want to highlight again because it's important to understand. So even at temperatures below the boiling points of compounds, students, I think, have a misconception that, let's say we're talking about water at 100 degrees Celsius, that at 99 Celsius, none of the water is going to boil. That's not true, right? 100 is when, well, okay. 100 is when it boils, I should say. It's not boiling at 99, it's boiling at 100. But this idea that I should say, let me use more proper chemical language here, that at 99 degrees, none of the water molecules are going to become gas. And that is not true, right? If you've ever cooked before, if you've ever cooked rice before, hopefully your parents have made you cook rice at least once, right? Stupid flies flying in front of me. If you've ever cooked rice before, you've noticed as the water is heating up, some steam from the water comes up before it gets to a boil. Okay? What that's telling you is as the temperature of the water is increasing, before you get to the boiling point, the vapor pressure of water is already increasing. So remember the definition of vapor pressure. The pressure exerted by the vapor in equilibrium with a liquid in a closed container at a given temperature. So, obviously uh, when you're cooking rice, you're probably not doing it in a closed container, right? But where you're monitoring and the whole kitchen is in a closed container, so you can really actually, measure vapor pressure. But you get the idea nonetheless, right? More gas molecules are going up into the air. So keep in mind that a liquid will have varying vapor pressures at varying temperatures, including below its boiling point. So a molecule with weaker intermolecular forces will have a greater vapor pressure at a particular temperature. So you can see here on this graph on the right, this is for water, and you can see the vapor pressure is rising, especially at about 50 Celsius, before we get to 100. Now, of course, once we get to 100, the vapor pressure really rises a lot, but even before we're getting there, like even at 50, the vapor pressure is starting to rise. A greater percentage of the water molecules are becoming gas. So let's look at an example of this boiling point in gas vapor pressure. So for example, 290 Kelvin and 1 atm, CBr is a solid with a measurable vapor pressure, whereas CCCl4 is a liquid. These observations provide evidence that under the given conditions, go ahead and read the answers, think about it, and pause me if you need to, and choose your answer. You know what? This is not a great example, actually, of this idea. I should have chose two things with that are both. I didn't look at this closely enough. I thought I changed it to something else. It should be two things that are both. Let's go ahead and answer this, and then I'll explain with another example quickly. So in this case, if we look at our periodic table, we can see that Br is lower than Cl, right? So since Br is lower than Cl on the periodic table, that means bromine's a larger atom, and so we know that the London dispersion forces are going to be greater. And in a problem like this problem, we're considering the strength of the intermolecular attractions. We're not considering the strength of bonds, so it's not C or D. And so the answer here is going to be A. That's why CBr4 is a solid and CCl4 is a liquid, because the intermolecular forces, chiefly the strength of the LDF among CBr4, is stronger. So sorry that if you were noticing, paying attention, I didn't include a good example of that. Ah, here it is. Okay, that's funny. Next slide. That's the real example. I just didn't get rid of that past one. Okay, here's a good example of boiling point in gas vapor pressure and understanding this idea in the context of AP Chem. So at 25 degrees Celsius, the following liquids have the indicated equilibrium vapor pressures. So this is the pressure they're exerting in a closed system as gases. Based on the data, which liquid has the weakest intermolecular forces? Okay. So weakest intermolecular forces means, we'll go ahead and actually pause this video, think about it, and then answer. Okay? So hopefully you've paused this video and thought about your answer. Weakest intermolecular forces means that it will most readily become a gas, which means that at the same temperature, a greater percentage of that chemical will be in the gaseous state. And therefore, the weakest intermolecular forces means the most gas, and therefore the most vapor pressure. So we're going to go with diethyl ethyl here. Diethyl ether. Okay, I'm going to end with some additional notes about how to handle FRQs that are looking at 3.1. So note that when identifying intermolecular forces in an FRQ, again, state all of them. I already said that, but like if it's water, don't just say hydrogen bonding, state all the ones that water's engaging in. If having to do with phase change, state how strong intermolecular forces mean more energy is required for phase change to be able to occur. Okay, so explicitly state that, right? If the molecules have a stronger attraction to each other, then it will take more energy to break that attraction and separate them going from a liquid to a gas. Okay? And therefore, it requires more energy to overcome that attraction because the attraction is stronger. And therefore, the particles have to have a greater average energy to move away from each other. And then explicitly state that all intermolecular, oh, hey, that's the same thing. Again, I guess I'll just say it one more time. Explicitly state all intermolecular forces every time in an FRQ. That is very important. So make sure you are doing that. Where if you're comparing three chemicals, right? Don't just say, well, water is hydrogen bonding. Also state, well, this other one only has LDF. And also, I should add actually here, compare size too. So if the main difference is not strength of LDF forces, show that you know that and say like the size of both of these molecules is comparable. So the difference in intermolecular force strength between them is not due to LDF, something like that. So you have to differentiate, is it because one has hydrogen bonding and the other just has LDF? Well, if it is like that, then you also need to say, right, if we're comparing, let's say, water and a similarly sized molecule, chemical A, and they both have about the same molar mass, you should say the LDF forces on both of these are really similar, but water has hydrogen bonding, so therefore its overall intermolecular forces are stronger, something like that. So again, state every molecule, if it's an FRQ, every molecule they're asking you to compare, state all the intermolecular forces happening in that molecule, and also be clear that you understand in your explanations that just because something has hydrogen bonding and something else doesn't, it doesn't mean that the intermolecular forces in the hydrogen bonding molecule are stronger, right? Make that explicit connection of LDF and size. So if they're comparable size and so LDF is not the main factor, state that. If one's way bigger than the other and so the LDF difference might be significant, state that. Okay? So state all the intermolecular forces every time. I think I'm repeating myself a little bit, but that's really important and you'll see that when you're looking at the practice problems, I think.